Hello, Algebra 2 students. Today, we have a lesson on probability. Now, you might know a little bit about probability already. Do you remember words like experiment, events, heads and tails, dice? Well, that's what we're going to talk a little bit about today. So first of all, I would like to introduce some of the equipment that we're going to use. For instance, here we have a die. More than one are called dice. The event that a die has can be 1, 2, 3, 4, 5, or 6. How many times I roll the die, each time is a trial. So if I roll this die and I get a 4, 4, 1, then I've done 3 trials. So my experiment is to roll the die. My event is whether I get a 1, 2, 3, 4, 5, or 6. And the trials are the number of times I do that. I can also flip a coin. And so I have a head or a tail when I flip a coin. And then a very popular experiment is to use a deck of cards. So here we have a Bengal deck of cards, and the card has 4 suits. We have hearts, clubs, diamonds, and spades. We have face cards, and we have numbered cards. And we have aces. So there are 4 aces, 4 twos, 4 threes, all the way up to 4 queens and 4 kings. So that makes 52 cards in a deck. So we're going to talk first of all about the counting principle. So let me share screen so that I can give you some notes on this. So first of all, we're going to talk about the counting principle. There are 2 ways of working with probability. One is to count the number of outcomes, and that's what we're going to do first. So here are some basic definitions that we're going to use. An experiment is the process by which I collect the data. So it's either finding different color of coins that I might chips. Okay, what's the probability of getting a white, a red, or a blue? It might be the coin, or it might be the dice, or a deck of cards. So there's all sorts of different ways, and many, many others besides that, to do an experiment. And then we have a trial. A trial is one event, and the more trials I do, the better my results will be. And then I have the sample space. The sample space is the outcomes that are possible. And the event is the particular outcome that I have. So events are subsets of the sample space. If an event has many different categories of outcomes, then the total number of outcomes that can result is the sum of all the possible outcomes. Now that might sound pretty complex, but basically it's just a matter of adding up all the outcomes and getting a total. So let's get some examples here. Flipping a coin, your outcome is heads or tails. Rolling a die, 1, 2, 3, 4, 5, 6. Picking a card, you have 52 different outcomes. Picking a disc based on the number of colors or however you distinguish different discs from each other. How many outcomes are there to picking a face card or drawing an ace? So what do we mean by picking a face card? How many face cards are there? Well, I have ace, king, queen, and jack. So I have 4 face cards, and then I have 4 suits. So if we consider the face cards only king, queen, jack, okay, then we have 3 face cards, and then we would have still 4 suits. Or drawing an ace. The ace, we have 4. So there are 12 ways of drawing a king, queen, or jack, and there's one way of getting the 4 ways of getting an ace. So we have 12 plus 4, okay? So our total is 16 total combinations. So that's what we mean by if an event has many different categories of outcomes, then the total number of categories or outcomes that can result is the sum of all the possible outcomes. Because it didn't matter if I got an ace or if I got a face card. How many outcomes when tossing a coin or throwing a die? Think about that. I'll give you a couple seconds. So when you toss a coin, how many outcomes do you have? 2. And when you throw a die, 6. So together, we have 6 plus 2, which is 8 total outcomes. Pretty easy stuff, right? Find the number of outcomes when using the number 1 to 20. So you choose when you're choosing a prime number or a multiple of 6 or a multiple of 10. So first of all, we have to determine how many possibilities in each one of these cases. So in each event, we have choosing a prime number up to and between 1 and 20, multiples of 6, up to including 1 and 20, and multiples of 10. So prime numbers, remember 1 is neither prime nor composite. So we have 2, 3, 5, 7, 11, 13, 17, and 19. There are 8 primes. And then multiples of 6, 6, 12, and 18. So we have 3 multiples. 10 and 20 are the multiples between 1 and 20. So we have 8 and 3 and 2, or 13 total outcomes. That's the counting principle. We count the number of outcomes in each one of the situations. Now we have another term, mutually exclusive. What we have been doing is counting all the outcomes when there was no overlap. But what happens if we have an overlap in the experiment, that the 12 appears both as a multiple of 6 and a multiple of 12 itself? Or what happens if we're talking about multiples of 2 and we have repeats with a prime number, which is also a 2? So that just means when we say mutually exclusive, that the outcome has nothing in common. None of the events have any common outcomes. So find the number of outcomes when using a prime number and a multiple of 6 and a multiple of 10. Well, when we did that, these were mutually exclusive. There was nothing that overlapped. But now I'm changing it. I'm saying, what is the number of outcomes possible when I choose a prime number, a multiple of 6, and a multiple of 4? Now when I do that, I don't have any overlaps between the prime numbers, but a multiple of 6 and a multiple of 4 that are common to each other is 12. So in the case of a multiple of 6, I have 3 outcomes. In the multiple of 4, I have 5 outcomes, but one of those outcomes is the same as the outcome for a multiple of 6. Now these events are not mutually exclusive. Multiples of 6 are not mutually exclusive from the multiples of 4 because there is an overlap. So in this case, the number of outcomes would be 6 plus 3 plus 5 minus the repeat of 12, And so I subtract 1 and I get 13 possible outcomes in this case. So when you count the total number of outcomes, don't forget to subtract off the number of repeated events or overlaps. Here's a helpful technique when you have more complicated events. So suppose that there are sandwiches offered in the cafeteria, that you can get turkey on rye or wheat bread, ham on rye or wheat bread, and chicken salad on rye or wheat bread. So how many different possibilities do we have? Well, we have 2 here, 2 here, and 2 here. So altogether, there are 6 different possibilities. A tree diagram helps us to organize ourselves so that we can count the outcomes more easily. Okay? So now life is going to become a little bit more complicated. Let's use the multiplication principle. Here's what the multiplication principle says. Suppose there are k items to be chosen. If there are A ways for item 1, B ways for item 2, C ways for item 3, and so on for k items. The total number of ways to choose k items is A times B times C, and so on for k items. What that means is that now we have many different events, and we want to choose from A, B, and C. So each one of them is a different event, and we're going to multiply them together to find out how many different combinations we have for the final event. Here's an example. A student is choosing a 3-letter password to use for email. Oops, that's not too secure, but for simplicity's sake, let us say only 3 digits in the password. How many passwords are possible if only the symbols that can be used with no repeats are capital A, small b, small c, 5, 7, asterisk, and pound sign? So there are 7 possibilities that you can use. Once you use one of them, you don't want to repeat. So 3 letters in the password. So the first time I can pick A, B, C, 5, 7, star, pound sign. So I can pick 7 possibilities. Okay. Now the next event, if I pick an A, I can only pick the remaining. If I pick a B, I can pick the remaining 6. If I pick a C, I still have 6 remaining to pick from. So the next time I choose a letter or a symbol for my password, I have 6 possibilities. The next time I've used 2 of them, let's say for simplicity's sake, I've used these first 2. How many do I have to pick from? 5. So to make my combination for passwords, I have 7 times 6 times 5, which is 210 possible passwords I can make up from these 7 possible symbols here. That's the multiplication principle. They're not individual events, but all of these are one event. The whole event is to make a password. And when I'm working with one event, then I multiply to find out how many combinations I can make, putting all of these symbols together as one event. But what I was doing with the addition principle is I was looking at separate events and adding up how many outcomes I could have of each separate event. When I add up the results of an experiment, that's the counting principle. But when I'm making up an event or one experiment, then I multiply between the combinations. How many possibilities are there if repeated values are allowed? So if I could repeat the symbols, if I could use pound, 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 or if I could use capital A, capital A, capital A, then if I pick 1, I would have 7, but then I could use that symbol over again. So I could use 7 and then 7. So I have 343 ways of having an outcome. Now we have one more idea to go. And it isn't a very complicated one, so it'll be a good note to end on. Independent and dependent events. So let's think about this. Independent and dependent. People sometimes confuse this with mutually exclusive, but they're not the same at all. So let's look and see if we can distinguish between them. An independent events are those that have no relation to each other. If I have one event like throwing a die and I'm flipping a coin, if I get a 6 on the die, it has no relation of whether I'm going to get a head or a tail here. Okay, they're totally independent. What I get on this is totally independent of what I get here. Okay, and if I pick a color here, okay, and then I put it back again, then the events are independent, okay? However, a good example of a dependent example is, what if I pick from a deck of cards a 10? And then I say, what's the probability of picking another 10? Well, if I haven't put this back, then it was dependent upon what I picked on my first time. For instance, if I picked a 10, I'm less likely to get another 10. Or if I picked an 8 the first time, and then I want to pick a 10, well, now I still have 4 10s left. So what I do on the first trial makes a difference on what I will get on the next time I pick. Those become dependent events. If I want to know what's the probability of picking a 10, and then I put the card back again, well, then it doesn't really matter what I picked the first time. Then it's independent. It does not depend on what I pick because I am putting the card back. But if I do not replace the card, then what I picked the first time makes a difference on how probable it is to pick the second time. Let's look at it with these chips I have here. Okay, I have 3 red, and let me just use 3 blue. Okay, now, what's the probability that I will pick a red? Well, 3 out of 6. Okay, I have 3 red and 3 blue. So I have a chance, a 50-50 chance of picking a red. What's the probability that I pick 2 red when I don't replace them? Well, the first time it's 50-50. Now, what's the probability that I get a red now? I'm more likely to get a blue. So this event is dependent upon what I did the first time. So that's a dependent event. But now look at this one. What's the probability that I get a red and I'm putting the chips back each time? Well, I pick a red. Okay, I had a 50-50 chance. But now I put it back again. What's the probability I get another red? It's independent because I had put the chip back again. All right. So those are examples of independent and dependent events. So the independent and dependent events means that the outcome of the first event can have an effect on the outcome of the second event. When it has an effect, it's considered dependent. When it does not have an effect, it is independent. Does flipping a head mean that I am more likely to get a tail the next time? No. As long as I have a fair coin here, I'm just as likely to get another head the second time. Both times the probability is 1/2. Head or tail, flip it again, head or tail. Does rolling a 6 the first time mean I'm more likely to get a 1, 2, 3, 4, or 5 the next time? No. Now, some people think that having a baby girl makes you more likely to have a baby boy the next time. Do you think that's true? So some events are independent, okay? And it depends upon sometimes how I set up the event, how I set up the experiment, whether I choose to replace or not replace. But for now, what you need to know is just the idea of independent or dependent. If I pick an ace from a deck of cards, then the next time I pick a card, am I just as likely to get an ace the next time if I did not replace the one I picked? No, you are exactly right. Unless I put the ace back, okay, I am less likely to get another ace because every other card has 4 choices. 10, 10, 10, 10. Okay. Jack of diamonds, jack of hearts, jack of spades, jack of clubs. But for the aces, I might only have an ace of diamonds, ace of hearts, and ace of clubs. So it is not as likely to get another ace. So you see, many ideas of probability have been studied, and you can see that they're not too complicated. And they can even be fun. So stay tuned for more upcoming lessons on probability in the future. Looking forward to seeing you again in class tomorrow. God bless you.